So we're going to look at one of the shorter topics in Year 12 chemistry called equilibrium. It's a topic that basically is about a type of chemical reaction which doesn't come up a lot in Year 12 chemistry. It's known as a reversible reaction, and that's where we'll start. Technically speaking, there are two types of chemical reaction in chemistry. The vast majority of them, in terms of what you come across in GCSE, are known as irreversible reactions. This is an example of an irreversible reaction. You've got magnesium with sulfuric acid forming magnesium sulfate plus water. The key thing that makes this an irreversible reaction is this bit in the middle. This arrow goes from the left to the right and doesn't go right back to left. In other words, once these two products are formed from the reactants, it's very difficult and sometimes impossible to get those products to go back to the reactants. So once it gets to the end, the reaction stops. Or in other words, once the products are formed in the reaction cannot then reverse and go back to the reactants. The second type of chemical reaction, which you see here is a reversible reaction, has one big difference in the middle with the arrows. These arrows here are known as reversible arrows. What they tell us is that once these two reactants react together to form the products on the right hand side, that product can then react and go back to the reactants. The reaction works in both directions. There's a definition for reversible reactions it'd be a good idea to know about. Basically, a reversible reaction is one in which the products, once they are made, can react to reform the reactants, which basically means go back to the start. There's one further piece of information you're meant to know about reversible reactions, and it's to do with exothermic or endothermic reversible reactions. Basically what we find is, and here's an example, if we just have A, which is a made-up chemical, reversibly going to B, which means B can go back to A at the end. If the forward reaction here, A going to B, for example, was exothermic, what we would find is the reverse reaction, which is B going back to A, would be directly opposite. In other words, instead of being exothermic, it would be endothermic. Just a quick reminder, exothermic means heat is given out in the reaction, so your surroundings get very hot. Endothermic means that heat is taken in during reaction, which means surroundings get very cold. Obviously this trend works both ways, so if the forward reaction was endothermic, the reverse reaction would be exothermic as well. It's always just opposites. Putting that into words, if a reversible reaction is exothermic in one direction, it will be endothermic in the reverse direction. There's only one further section to look at in the equilibrium topic, and it's a concept known as dynamic equilibrium. What dynamic equilibrium is about is basically what reversible reactions look like when they are done in real life. I'm going to use a very simple example to explain this. Let's again imagine we've got a made-up reaction. We've got a chemical A, which can reversibly go to B, which means B can go back to A at the end. Now let's imagine I actually want to do this chemical reaction. So I get a container and I put some molecules of A into the container. Now, one wee point we'll come back to, this container is referred to as a closed system. That means that nothing can actually get in or out of this container once I've put my chemicals in at the start. This is kind of important for forming a dynamic equilibrium. Now, once these chemicals are in, this A can react to form B. So if I leave it for a few seconds, then come back to it and look at it, it might look like this. What we see here is that some of the A has turned into B. Now, if I leave this for a little bit longer, as you might expect, some more A can turn into B as well. But also, because this reaction is reversible, some of the B can turn back into A. So now in this last box, we've got a different arrangement. It's still a mix of A and B, but different parts of the mixture are A and different parts of the mixture are B. Basically what happens here is that because A can turn into B and B can turn back into A, both of those reactions, forward and reverse, happen at the same time, and basically their effect cancels out. What we'll be left with here at the end is some sort of mixture of A and B, which is staying kind of consistent. So the amount of B and the amount of A kind of doesn't change too much, because the rate at which B is turning into A and A is turning into B cancels out. They're kind of equal rates. So to put it a little bit more simply, in this last box, the amount of A and B is staying constant, but that doesn't mean the reaction has stopped. Both reactions are still happening, just at the same speed. So A is going to B at the same speed at which B is going back into A. All that leaves us with is a definition. You're meant to be able to explain to the examiner what is meant by the phrase dynamic equilibrium. There are 3 parts to this definition. It's quite a long one. The first bit is, it takes place in a closed system. That means a dynamic equilibrium doesn't really work really well if stuff can escape. So it needs to be enclosed. Nothing can get in, nothing can get out. The second part is that the rates of the forward and the reverse reactions are equal. So in our little example, that just meant the speed at which A was turning into B was exactly matched by the speed at which B was turning back into A. And the final part is, this means that the amounts of the reactants and the products remains constant. So back to our example, that meant at the very end that the amount of B and A in this box, even though the molecules are still changing, isn't actually changing overall in terms of the amount of A and the amount of B. So if you're ever asked to define a dynamic equilibrium, you just need to make sure you write down the following 3 points.